Good morning, students. Today we are going to discuss about the alkanes, chemical properties. Continuation. Yesterday we have discussed a few chemical properties. The rest of the properties today we are going to discuss. The first one here. Today's our topic. The first chemical property is addition of sulfuric acid. Addition of sulfuric acid. Alkanes on reaction with cold concentrated sulfuric acid form alkyl hydrogen sulfates. Alkyl hydrogen sulfates. And let's see the reaction. The first step, sulfuric acid, it ionizes to form H plus and HSO4 minus ions. This is proton and this is bisulfate ion. Now it will be in the form of this ion, sulfuric acid. Now let us see the reaction. Overall reaction of alkene with sulfuric acid. This alkene, C double bond C. This is sulfuric acid, H2SO4, 2 hydrogens, 4 oxygens, 1 sulfur, H2SO4. Then the product obtained is H of the sulfuric acid goes to one carbon, and then the rest of the part, that is HSO4 minus, goes to another carbon, and this pi bond breaks and two new sigma bonds are formed in between the doubly bonded carbon atoms. So one with the hydrogen, the other one with bisulfate ion. So like this, one pi bond is broken from in the alkene, and two new sigma bonds are formed in the product. So this is addition reaction, and it is electrophilic addition reaction we said yesterday, because the electrophile initiates the addition reaction. Okay, so the product is alkyl hydrogen sulfate. This is alkyl hydrogen sulfate. This is all alkyl group and hydrogen sulfate. This is all alkyl group, this one, and this is hydrogen sulfate, alkyl hydrogen sulfate. Is It is also known as ester of sulfuric acid of alkanes. Ester of sulfuric acid of alkanes. This is sulfuric acid ester of alkanes. Let me see. Okay. So this is uh, another chemical property of alkanes, that is addition of sulfuric acid. So when sulfuric acid is added to alkanes, what happens? We will get alkyl hydrogen sulfate. Alkyl hydrogen sulfate, or it is also known as sulfuric acid ester of alkanes. Now let us discuss the mechanism. So the mechanism involves addition of hydrogen to one carbon atom of the double bond and bisulfate ion. This is bisulfate AG, bisulfate ion to the other carbon atom of alkane to get the product. Now let us consider the steps involved in this reaction mechanism. In the first step, the pi bond of this alkene, it abstracts the proton from sulfuric acid. Then what happens? The proton forms a bond with one doubly bonded carbon. The other carbon gets the positive charge with three sigma bonds, positive charge. This is nothing but a carbocation or carbonium ion. What is carbonium ion? We said this is nothing but the ion in which carbon bears the positive charge. This is carbonium ion or carbocation. It is also called. Now, in the next step, this carbocation, with this carbocation, the rest of the part of the reagent, that is the nucleophilic part of the reagent, that is bisulfate ion, it attacks the positively charged carbon or carbocation. Then what happens? We will get the final product, that is the sulfuric acid ester of alkanes is obtained as an addition product. It is obtained as an addition product. Okay. So now let us see the reaction. One specific example. So here we are considering an unsymmetrical alkene, that is propene. Unsymmetrical alkene, propene we considered here. Why it is called unsymmetrical? Because this carbon has two hydrogens attached to it, whereas this carbon, doubly bonded carbon, this carbon, it has one hydrogen and one methyl group. Therefore, whenever two doubly bonded carbons, they have dissimilar groups, it is known as unsymmetrical alkene. If they have similar groups, then it is called symmetrical alkene. So this propene is the best example, the simplest example for the unsymmetrical alkene. So when this is, propene is treated with 80% sulfuric acid in the cold condition, then what happens? The H plus of this HTSO4 goes to one carbon, one carbon. If it follows Marconikov's rule, the H plus, the positive part goes to the carbon with more number of hydrogens, and the negative part, that is HSO4 minus 8, this goes to the carbon with the less number of hydrogens. So as per Marconikov's rule, um, the alkene, this propene, it combines with 80% sulfuric acid to form this compound. So in this compound, the H plus of H2SO4 is added to this carbon, the terminal carbon, and HSO4 minus ion goes to the middle carbon because it is the secondary carbonium ion produced, and, which is more stable than primary carbonium ion. Therefore, this is the major product obtained. And this alkyl hydrogen sulfates, when they are subjected to hydrolysis, then what happens? Alcohols are obtained. So here you see, instead of HSO4 minus ion, we have OH. So this is in this way, this propane, when it combines with sulfuric acid, we will get the alkyl hydrogen sulfate, the, which on hydrolysis produces isopropyl alcohol as a major product. Now, next one, anti-Marconic addition, that is free radical addition of HBr. So, free radical addition or anti-Marconic addition, what happens in that and which is the major product, that let's discuss. So here MS Karash and FW Mayo, they showed that the results of addition of HBr to unsymmetrical alkene in presence of a peroxide is opposite to Marconikov's addition. So this is known as anti-Marconikov's addition, and it is also known as peroxide effect, or it is also called Karash effect. It is called Karash effect or peroxide effect or Marconikov's anti-Marconikov's addition. So in anti-Marconikov's addition, what happens? Let us see with an example. So peroxides, they produce free radicals and they act as catalysts to accelerate the addition reaction. So in this reaction, in presence of a peroxide, if a reagent like HBr is added to an unsymmetrical alkene, what happens, that we will discuss here. So here peroxides, they produce free radicals. Peroxides, they produce free radicals. They act as catalysts to accelerate the addition reaction. So if HBr is added to this alkene, this we have already discussed. Marconikov's addition we have already discussed. Then what happens? The negative part goes to the carbon with less number of hydrogens. That is Marconikov's rule says. But here, in presence of peroxide, what happens? That let us see. So this is a symmetrical alkene. Then what happens? H goes to one carbon, Br goes to another carbon, and we will get an addition product. Here we did not mention any groups attached to doubly bonded carbons. That is in this alkene. So let us say like this, the addition takes place. Okay, H to one carbon, Br to another carbon, and two new sigma bonds are formed, and the pi bond present in the alkene is broken because it is an addition reaction, and this addition takes place in presence of peroxide. This peroxide, it produces free radicals which act as catalysts and they accelerate the addition reaction. Now let us see mechanism. In this, addition of HBr to an unsymmetrical alkane is a free radical chain reaction. It's a free radical chain reaction. So what are the steps involved in the chain reaction? Let us see. First step is chain initiation step. So in this chain initiation step, this free radical, this peroxide, it undergoes ionization to form uh, free radicals, alkoxy free radical. This is alkyl group, this is oxygen, alkoxy free radical. So the homolytic bond fusion produces free radicals, we know. Now here the bond breaks, this bond breaks, and this RO will have one electron and this RO will have one electron, that is two alkoxy free radicals are produced. Now, in the next step, in the initiation step itself, what happens? This alkoxy free radical, it abstracts a proton from HBr, that is the reagent, to form R over H and Br dot, that is bromine free radical, is generated. So, addition of HBr to an unsymmetrical alkene is a free radical chain reaction, we said. This chain reaction will have three stages: the chain initiation, chain propagation, and chain termination. Now here we discussed about the chain initiation. In the initiation reaction, what happens? The peroxide, which undergoes ionization to form alkoxy free radical, and this alkoxy free radicals, they act as catalysts and they accelerate the reaction. Here, this alkoxy free radical, it combines with the reagent HBr and abstracts H dot, that is hydrogen atom or hydrogen free radical, to form R, O and H, and this Br with one electron is produced as a bromine free radical. Now, this bromine free radical, it propagates the chain. Now, let us see the chain propagation reaction. So, this bromine free radical, it propagates the chain. It forms a bond with one of the doubly bonded carbons with the help of the pi bonded electrons. Pi bond over here, a pi bond is present which has two electrons. With the help, it utilizes one electron from this pi bond to form a bond with one of the carbon atoms. See, here a bond is formed in between the carbon and bromine. And the next carbon will be having the rest of the electron. You can see here, this is a carbon free radical is produced here. Okay, carbon with odd electron or unpaired electron is a carbon free radical here produced. So, alkyl free radical is produced here. Now, this alkyl free radical, once it is produced, it abstracts a hydrogen atom. It abstracts the hydrogen atom from HBr, that is the reagent, to form a bond between this carbon and this H. C and H bond is formed. And this Br free radical is regenerated, and this participates in the first step. So, this reaction, chain reaction, it propagates these two reactions, second and third reactions, they repeatedly take place to form the product. So the product is obtained in which hydrogen gets added to one carbon and Br added to another carbon of an alkene. So the final product is an addition product obtained, an alkyl halide addition product. So here like this regenerated Br dot, that is bromine free radical, attacks another molecule of alkene and continues the chain reactions. Okay. So like this, the chain reaction propagates. Now let us see one specific example. See, this is the specific example. In this specific example, we considered unsymmetrical alkene, that is RCH double bond CH2. If this R is CH3, that becomes propane. Okay, propene. This is the simplest unsymmetrical alkene, propane. If R becomes CH3, it is propane. Okay, R can be anything. So this is one alkene we considered. To this we are adding HBr in presence of a peroxide. Then what happens? This H goes to one carbon and Br goes to another carbon. So which is the major product? That is more important here. So in presence of a peroxide, what happens? The negative part of the addendum goes to the carbon which contains more number of hydrogens. This is opposite to Markovnikov's rule. In the Markovnikov's rule, we said the negative part of the addendum in the sense the one which is to be added, that is nothing but the reagent. Okay. So from this HBr, Br should go to the carbon containing more number of hydrogens according to peroxide effect or Kharash effect or anti-Markovnikov's rule. Whereas in the case of Markovnikov's rule, we said that negative part goes to the carbon containing less number of hydrogens. But here, in presence of peroxide, as it is a free radical mechanism, what happens? The bromine free radical, it goes to the carbon containing more number of hydrogens. Okay. Then we will get secondary, when this bromine it goes to this carbon, we will get the bromine to this carbon, that is the terminal carbon, and H that is hydrogen atom of this HBr, it goes to, that is positive part of this HBr, it goes to this, that is middle carbon. Thus we get RCH2 CH2Br, that is one alkyl bromide is obtained as a major product. So as this addition takes place via more stable free radical intermediate, as this addition it takes place via more stable free radical intermediate. So this is the major product obtained. So the stability order of free radicals is tertiary greater than secondary, which is greater than primary. Okay. Now let us discuss the addition of HBr in presence of peroxide to an unsymmetrical alkene with a specific example. Now, let us consider this example. This is 1, 2, 3, 4. This is butene, 2 butene, 2 methyl, 2 butene. It is 2 methyl, 2 butene. So, here this is the tertiary carbon and this is the secondary carbon. So, in between secondary and tertiary carbons, a double bond is present. Then this Br dot, it goes and attacks at either this carbon or this carbon. Then the bond is formed in between. The first example, let us consider in this, the bond is formed in between the secondary carbon and bromine. We will get this free radical. If this goes and attacks this carbon, then what happens? A bond is formed in between tertiary carbon and bromine. Thus, we get this free radical. Okay. Now, if bromine goes to this carbon, this is the free radical obtained. This is a tertiary free radical which is more stable. If bromine goes to tertiary carbon, that is this carbon, we will get this free radical here, dot, you can see secondary free radical which is less stable. So always more stable free radical is produced, more stable free radical is produced. Therefore, this will be the major product. That is the H dot of this HBr, it goes to this carbon and we will get this as a major product, this alkyl halide. Okay. So this is now let us see the here this H dot, that is hydrogen atom, it goes to this carbon, then we will get this as a major product. Okay, so always more stable free radical is produced during the addition of HBr, therefore we will get a major product according to anti-Markovnikov's rule. Okay, now let us see the next property of alkenes, that is trans addition of halogens and its mechanism. So, trans addition of halogens and its mechanism. So, what happens here? Let's trans addition. So, addition of halogens to alkenes forms vicinal dihalides. Vicinal dihalides. What are vicinal dihalides? We say vicinal dihalides means the halogen atoms are present on adjacent carbon atoms. Then it is known as vicinal dihalide. Adjacent. పక్కన కార్బన్స్ పైన రెండు halogens atoms ఉంటాయి. They are called vicinal dihalides. In the other way, if the both the halogen atoms are present on the same carbon, then it is known as geminal dihalide. Okay. Here we got vicinal dihalide because two halogen atoms are present at adjacent carbon atoms. Okay. So addition of halogens to alkenes forms vicinal dihalides. Now this is an alkene. We are adding a halogen. Halogen, it can be chlorine, it can be bromine, it can be iodine. Okay. Then what happens? One X atom goes to this carbon, another X atom goes to this carbon. Then we got vicinal dihalide. Here we wrote X atom to this carbon on this side, whereas another X atom, that is halogen atom, added to this carbon from the back side. You can see here. Both the X atoms here I did not write. Here we wrote. Why? Because it is trans addition. Trans. Okay, trans, opposite. This is anti-addition or trans addition. So trans addition or anti-addition means what? That we will discuss in detail with the help of an example and its mechanism. Okay, so addition of halogens to alkenes forms vicinal dihalides. Vicinal in the sense the halogen atoms are present on the adjacent carbon atoms. Here we said trans because they are anti or opposite to each other, these two halogen atoms. Okay, now let's see the mechanism. In this, first step involves formation of halonium ion. Formation of halonium ion. Now, this is alkene, this is X2, that is halogen. With the help of the pi bond electrons present in between the two carbon atoms, it abstracts this X plus. Okay, then we can see this. A cyclic halonium ion, cyclic. Okay, three-membered ring is formed. Halonium ion is produced as an intermediate and this X minus is coming out. This X along with this pair of electrons in the form of X minus, it comes out, and this with another X, this forms a bond with one of the carbon atoms. Actually, once this is the cycle or the ring is broken, this halogen atom gets bound to one of the carbon atoms. But here initially what happens, this pi, with the help of this pi bond electrons, it forms a bond with one of the X atoms of X2 molecule to form a cyclic halonium ion. Cyclic halonium ion. This is the first step. Now in the second step, what happens? Let's see. In the second step, opening of halonium ion. So opening of halonium ion. So X minus, which is produced in the first step, it attacks from the back side. See, this X minus, it goes and attacks one of the carbon atoms from the back side, because this front side already this is cycle or this ring, three-membered ring is present. So this X minus, it goes to this one of the doubly bonded carbons from the back side to form a bond. Okay, to form a bond. So now we can see this bond breaks and a new bond is formed in between carbon and the CX. CX, new sigma bond is formed, and this bond breaks, and those electrons are taken by this X, and it loses this positive charge, and this bond is retained, CX bond. So in between this carbon and halogen, one sigma bond is formed, new sigma bond, and in between this carbon and halogen, another new sigma bond is formed, and the pi bond present in between the two carbon atoms in the alkene is broken. Okay, so like this is trans addition or anti-addition. Both the halogen atoms are anti or opposite to each other. Okay. Now, next one is anti or trans addition of peracids via epoxidation. So, epoxide is the cyclic oxide which is obtained as an intermediate during the addition of peracid to an alkene. What is peracid? Acids we know. Similarly, peracid in this, per in the sense extra, excess, more. So, more number of oxygen atoms are present in that acid, then it is known as peracid. Okay. Now let's see, the conversion of alkenes into epoxide is called epoxidation. Conversion of alkenes into epoxide is known as epoxidation. What is epoxide? We said this is cyclic oxide is called epoxide. So epoxide is the three-membered oxygen heterocyclic compound. Epoxide contains three members and three atoms are present. Out of the three atoms, two are carbon atoms and one is oxygen atom. Three-membered oxygen heterocyclic. So in that, in those three members, one is hetero atom, that is oxygen. It is a cyclic compound. So oxygen heterocyclic compound. So peracids are the oxidizing agents which convert alkenes into epoxides. So peroxides They are nothing but oxidizing agents. They convert alkenes to epoxides. So oxidizing agent in the sense which gives oxygen to alkene to form an epoxide. So peroxy acids such as peroxybenzoic acid. Peroxybenzoic acid. Benzoic acid is C6H5COOH. Peroxybenzoic acid is C6H5COOH. One oxygen extra. Okay. Peroxy bond is present. OO bond is called peroxy bond. So in per acids, peroxy bond, peroxy linkage is present. And example for peroxy acid is peroxybenzoic acid, peroxybenzoic acid, and next one is metachloroperoxybenzoic acid. So on benzene ring, meta position chlorine atom is present. So metachlorobenzoic acid can be used in non-nucleophilic solvents such as carbon tetrachloride. So this peroxybenzoic acid or metachloroperoxybenzoic acid or metachloroperbenzoic acid can be used in the solvents like carbon tetrachloride to produce epoxides in the good yields. So backside attack of the ring by water produces transglycol. Now let's see the reaction with the help of an example. Here it is a general reaction we consider. In this is alkene, C double bond C, alkene. It is treated with a peracid. RCOOH is acid, whereas RCO taken thrice into three oxygen atoms are present here. So RCOOH it is. So this is peracid. Then what happens? It gives one oxygen to this. It oxidizes alkene to epoxide. This is only epoxide. This epoxide, it has a heterocyclic ring system. Heterocyclic molecule it is. Hetero in the sense one hetero atom other than carbon is present in that. That is nothing but oxygen here. So it is oxygen heterocyclic compound. It is a three-membered ring. So this ring contains only three members: one carbon, another carbon, and oxygen. Two carbons and one oxygen. So and this is this. Peracid, it gives one oxygen to alkene, and alkene becomes epoxide, and this peracid becomes acid RCOOH. It is nothing but acid. Now let us see the mechanism of this trans addition of peracids. There the first step is epoxide formation. Step 1 is epoxide formation. This uh, in this how epoxide is formed is given here. So this is RCOOH. This is peracid. RCO3H or RCOOH. This is peracid. So this oxygen is extra. Otherwise, it is nothing but an acid. RCOOH is an acid. Here, carboxylic acid. Here, one oxygen extra. Therefore, it is called peracid. So this peracid, it reacts with this alkene. It reacts with alkene to form a bond between this carbon and this carbon. So this oxygen atom, it forms a bond between this carbon and this carbon to form, see, this is the intermediate produced, okay, transition state we can say, and finally we get this, what do we say, epoxide, and this RCOOH is the acid produced. So per acid, it combines with alkene with a, to form an epoxide through a transition state, and acid is generated here. So this is step 1, epoxide formation. Now in the second step, what happens? Opening of epoxide gives trans addition product. Opening of epoxide, it forms a trans product. So here ring can be opened up in both acidic and basic medium, following SN2 mechanism. What is SN2? We know it's a substitution nucleophilic bimolecular reaction. So by this method, the ring opens in acidic or basic medium. Now let's see, this is the epoxide. Now this is acid we have considered in the first step. So this forms with the help of this lone pair of electrons present on oxygen, it extracts this proton to form OH bond. this is protonation of this epoxy oxygen. Protonation of epoxy oxygen takes place, and this oxygen with three bonds, it bears the positive charge. Now, what happens? The ring opening takes place by the water molecule that is present in the medium. This is present as a medium in the acid. So this goes and attacks the one of the carbon atoms from the back side, because the one side this group is there, this ring is there. Let me see. Okay. Then what happens? This goes and attacks this carbon from the back side. Then what happens? Here this bond breaks, and here OH2, this carbon, and another OH from this H2O to this carbon are formed. Thus, this is transposition, that is antiposition. Two OH groups are present opposite to each other, and whenever two OH groups are present and the adjacent carbon atoms, then it is known as glycol. So glycol. So this is trans glycol. Two are present, two OH groups are present on the same side, then it is known as syn glycol, syn or cis. Okay, so this is trans glycol. So in this, transglycans are produced in acidic as well as basic medium. Here we discussed about acidic medium. In the basic medium, what happens? So in the basic medium, this base, that is OH minus, it goes and attacks one of the carbon atoms, any carbon, from the back side. Then what happens? This bond here, the bond here breaks, and it abstracts the proton from water to form OH here, and this OH forms a bond to this carbon. So OH and OH, that is once again glycol. It is called trans because they are opposite or anti to each other. Okay, so like this, uh, per acid addition via epoxidation is a trans addition. Trans addition or anti addition, we can say. Okay, right. Now let's see the next chemical property of alkenes, that is cis addition of alkenes, cis additions, syn or cis addition. The first example here we are going to consider, that is syn hydroxylation. Syn hydroxylation, that is hydroxylation in the sense addition of OH only. Two OH groups are added to adjacent carbon atoms, that is the doubly bonded carbon atoms, in syn direction or cis direction. So here the syn hydroxylation, the two OH groups are present on the same side of the double bond. Then it is known as syn or cis addition. So the common reagents for syn hydroxylations are potassium permanganate KMnO4 and osmium tetroxide OSO4. OSO4. Anyone can be used. Okay. Now here let us see the, that is common example, general example. This is an alkene, a general alkene we have considered. Here OSO4 is added. OSO4, after the addition of OSO4, it should be hydrolyzed to get the final product, that is syn hydroxylation product we should get. Okay. So two OH groups on the same side of the double bond, same side of the double bond. Then here the pi bond breaks in the alkene, and two new sigma bonds are formed in between the two doubly bonded carbon atoms and two OH groups. Thus, the final product is obtained, that is glycol, syn glycol is obtained. Now, let's see the mechanism. Osmium tetroxide, it reacts with the alkene in a concerted step. In a concerted step, single step, we mean to say. Concerted step to form a cyclic osmate ester. A cyclic osmate ester is produced as an intermediate by the action of osmium tetroxide with alkene. As the two carbon oxygen bonds are formed simultaneously to form cyclic osmate ester, the oxygen atoms added to the same face of the double bond. At the same time, the bonds are formed in between the doubly bonded carbons and oxygens of osmium tetroxide simultaneously, that is at the same time. Then what happens? Both the oxygen atoms of osmium tetroxide are added to the alkene on the same side. same face at same side of the double bond. That is, they add with the syn stereochemistry or cis stereochemistry. Thus, this hydrolysis of osmate ester thus formed produces syn glycol or cis glycol. Okay. Now let's see the mechanism here. This is C double bond C alkene. This is osmium tetroxide OSO4 osmium and four oxygens with the double bonds. Then with the help of this double bond, it forms a bond in between this oxygen and this carbon. With the help of this double bond, it forms a bond between this carbon and this oxygen. See the bond? New sigma bond is formed between carbon of alkene and oxygen of osmium tetroxide. And here also a new sigma bond is formed in between oxygen of osmium tetroxide and this carbon. See, two new sigma bonds are formed and pi bond is broken. This pi bond is broken. Now we get this. This molecule is obtained. Now this is osmate ester. Cyclic osmate ester is produced. This cyclic osmate ester it undergoes oxidative or reductive decomposition, either oxidative or reductive decomposition to form, that is the bond here, this bond breaks to form a syn or cis glycol, Here the specific example we have given, this is a cyclohexane. It undergoes syn hydroxylation with osmium tetroxide to form a syn or cis or syn product. Okay. So this is cis addition of alkanes. One example we have given, that is action with either potassium permanganate or osmium tetroxide. Both will give cis products. Now, here permanganate hydroxylation. Previously, we have discussed about osmium tetroxide hydroxylation. Here, permanganate hydroxylation. A cold dilute solution of potassium permanganate, it hydroxylates, that is, it adds two OH groups. We mean to say hydroxylates, hydroxyl group, that is OH group. Hydroxylates alkenes with cis or syn stereochemistry, similar to osmium tetroxide. Okay. So KMnO4 also adds to alkene and forms a cyclic manganate ester. In the case of osmium tetroxide, cyclic osmate ester is produced. Here, cyclic manganate ester is produced. And the basic solution hydrolysis, that is, in presence of a base, it undergoes the cyclic manganate ester undergoes hydrolysis to form um, uh, glycol. To form glycol, that is, the basic solution hydrolyzes the manganate ester, liberating glycol. Okay. So here alkene we consider a general alkene, KMnO4 and a basic hydrolysis, base and water. Okay. So initially it combines with this alkene to form a manganate ester, which undergoes hydrolysis in presence of a base to form finally a syn glycol, syn or cis glycol. Syn or cis in the sense two OH groups are present on the same side of the double bond. Okay. When they are present on the same side, it is called syn. When they are present on the opposite side, then they are called anti or trans. Anti or trans. Now let's see the mechanism of this reaction. So here we can observe this is alkene, this is manganate ion, permanganate ion. Okay, KMnO4, K plus is removed. This is O minus, MnO4 minus. So permanganate ion. So with the help of this bond, it forms a bond in between oxygen of MnO4 minus and carbon of this alkene. And with the help of this pi bond, it forms a bond in between, a sigma bond in between carbon of alkene, this carbon of alkene and oxygen of MnO4 minus. You can see a new bond here, carbon and oxygen, carbon and oxygen. As this is taking place simultaneously, the two bonds are formed at a time. They are present on the same face, same side. Okay, because of that reason only we are able to get the syn glycol or cis glycol. So this is the step one. That is manganate ester is produced. And the step two, this is the step two. In the step two, what happens? This manganate ester, it undergoes basic hydrolysis. That is, in presence of a base, it undergoes hydrolysis. That is, in presence of water, breaking up of the bonds takes place. Here the bond breaks and H we will get, and here the bond breaks and another H we get here. Then what do we get? A syn glycol. Syn or cis glycol is produced as a final product. So this is the reaction mechanism where an alkene combines with potassium permanganate to form a manganate ester, and this manganate ester, it undergoes basic hydrolysis to form a syn glycol as a final product. Okay, this is about the reaction mechanism of permanganate hydroxylation. Permanganate hydroxylation. Now let us see the different questions related to today's topic. So here we have given an alkene, an alkene. So this is the cis alkene. So to this is CH3, CH double bond, CH, CH3. Okay, this is nothing but 2-butene, 2-butene, cis-2-butene. To this, if we add CPBA, CPBA is metachloroperoxybenzoic acid, metachloroperoxybenzoic acid. So what is the function of metachloroperoxybenzoic acid? It is a peracid. It adds two OH groups, two OH groups to alkene, okay, in the trans manner. So when this is added, and in the next step after the addition, the second step, it undergoes what do we say, initially epoxide is formed. In this next step, what happens, epoxide um, undergoes ring opening from the back side with the help of either acid or base to form a trans glycol. So you predict the product produced in these two reactions. So this is trans hydroxylation. Trans glycol is produced in these two reactions. So what are the products obtained here in this reaction and this reaction? You try to solve this. So this is cis-2-butane. This is trans-2-butane. So to this we have added the metachloroperoxybenzoic acid and acidic followed by acidic hydrolysis. And next question. mm, Give any two methods for the preparation of olefins with suitable examples and mechanism. And next one is what is Marconikov's rule in addition of alkenes. Discuss with suitable examples. Marconikov's rule, addition reactions. We have discussed many. Addition of HX, addition of H2, addition of water, addition of HOX. Many reactions we have discussed. And next one is explain the following. That is trans addition of bromine to olefins and cis hydroxylation with KMNO4 or osmium tetroxide. So, trans hydrox addition of bromine to olefins. Just now we have discussed, that is addition of X2. Addition of X2. There also what happens, halonium, cyclic halonium ion will be produced, and afterwards a halonium ion opens with the help of X minus from the backside attack to form trans dihalide. Vicinal dihalide is produced, which is trans dihalide. So trans addition of halogens here we should discuss, that is bromine as an example we have taken, and cis hydroxylation with KMNO4 and osmium tetroxide. Just now we have discussed osmium tetroxide and potassium permanganate. They form the syn or cis glycols, syn or cis glycols. So that we should discuss here. So these are the different questions we come across in this topic. That is alkenes preparations we have already discussed, and few properties also we discussed yesterday, and today's topic is the rest of the properties of alkenes. So in this cis hydroxylation, syn trans hydroxylation we have discussed, and anti-Markovnikov's rule we discussed, anti-Markovnikov's rule, addition of HBr to unsymmetrical alkenes, all these properties today we have discussed. Okay, thank you. We will continue this same topic, that is the rest of the chemical properties of alkenes we should discuss in the next session. Okay, thank you once again.